All right. Hello and welcome to our first programming task. Today we're going to talk about arrays. We're going to talk about the runtime, performance of arrays a bit, and we're going to talk about a few operations, let's say, with arrays that you're probably already familiar with, but we're going to do a little bit of a deeper dive into them and maybe look at a couple of alternative ways to do them. So arrays are a data structure that I expect everybody to already be familiar with, so you shouldn't be learning anything new today except maybe how to contextualize some of the things you already know about arrays in terms of analyzing their runtime for thinking about big O notation in the future. And we're going to start with this pretty big example that I've built. We're mostly looking on the left here today. Sometimes I'll try to tile things into different windows, but yeah, today will be mostly on the left. There are a lot of other pieces to this demo that are all part of the display. All of it comes together to create this. The grid that you see on the left there is for inserting things into the array. The array is shown visually by these two black bars here. So that black bar marks the beginning of the array, that black bar marks the end. The visuals aren't really important here, but I am obviously going to provide all of the source code to you so you can peek under the hood, use all this for your homework or whatever. This is all built with Swing. By default, it's in insert mode. I can use the A, S, D, and F keys to switch modes. That changes what clicking on these is going to do. Today we're just going to deal with insertion and removal, which are A and S in this demo. And this little pink box is tracking something that I call next spot, which I'm going to talk about later as we go into the demo some more. So I think that's it to get you into it. Again, don't have to look at the display too much. It's kind of irrelevant here, and we'll probably use this display again for some other data structure examples that we look at later on. So like array lists, for example, which we'll look at next week. All right. First, let's look at insert. So I've got a couple of, let's call them flags that change the way that insertion is going to work. If you look at the window on the right, I have insert is sorted. Is sorted as a variable in the display that you can pick. That was kind of lazily done. Don't worry about it. But when you make a new array demo, which is the thing that's actually getting rendered to the panel, you get to decide whether it's going to be sorted or not. Again, a little bit lazy, but it's fine. So is sorted is going to determine whether or not we're going to use a sorted array or an unsorted array. So our sorted array is going to be sorted into ascending order, so 0 is the smallest, and then 1, then 2, then 3, then 4. So if you were to try to insert, let's say, 2 into 1, 3, 4, 5, 6, I think we all know that it's going to go 1, 2, 3, 4, 5, 6, right? It's going to be inserted into that spot. Whereas if you're inserting 2 into an unsorted array, then it's just going to go in the next available spot, so on the end there. You'll end up with 1, 3, 5, 6, 2. So I think everybody kind of intuitively understands that. I'm also using another if-then statement when we get to the unsorted better and worse, or better and normal variants. We'll look into that a little bit more in a bit, but basically I want to show you two ways to do insertion and removal. So there's going to be the easiest way and then the better way, maybe from a runtime performance perspective. So let's actually start with the simplest of all. Let's start with just inserting something unsorted into an array, and we're going to do the not better one. So the easiest way to insert something is to loop through the thing, equals 0, is less than r.length, I plus plus. So we loop through the whole length of the array, and then we're going to find the first empty spot available, and if we find one, then that's where we put the thing we're trying to insert. So n, the argument here, is the value that we're trying to insert, and this is an array of integers for simplicity. So later on, we'll do some more complicated object arrays, but we're starting out with just integers. And I've also created this placeholder for the default value. So to avoid using 0, we're making it so that the default value is -1. We're also going to use this as the default value for an invalid index. Obviously, -1 is an invalid index. And so when I initialize the array, everything is set to the default value. if the display sees that something is the default value, it just leaves it blank. So you'll see no square for things that are the default value. But all right, we're going to go through the array. We're going to find the first available spot. I'm saying that something that is the default value is the available spot. There are no null ints, right? So if this was an object array, we might look for the first null spot, for example, but here we can't do that because there's no null integer, but we got this placeholder value that signifies that it's empty instead. I don't know why I keep saying k here. And then r of I is equal to n. Okay, now if this loop gets to the end and we haven't found the thing that we're looking for, the empty spot, then the array must be full. So there were no empty spots. We can't insert anymore. We'll print an error. So we're just going to print array is full, can't insert. All right, and I have everything set to use this one. I gotta set use better to false because I haven't written the better one yet. So let's give it a try and that seems incorrect, doesn't it? Whoops. Well, what did I forget to do? Well, I didn't escape the for loop, did I? So it's just gonna keep going, find all the other empty spots and insert it into those. So of course, once I found the spot where I want to insert into, I return. All right. Now, there's 4, there's 5, there's 2, there's 1, there's 0, there's 3, there's 7. It's pretty easy. It just inserts them up to the end, and then when we get to the end, it just prints in the console, array is full, can't insert. Okay, lovely. This is okay, except that the insertion time itself, right? Let's make this into a comment. So this inserts an item into the first spot available. So the insertion time itself, with what we learned about Big O the other day, that's constant because nothing is shifting to make room for it. It's just one operation. It doesn't matter if there's a billion items or, 10 items or something. It doesn't matter. We're just inserting it and then we're not moving anything else. Nothing else happens. And the insertion itself is constant time. And by the way, I'll leave more detailed version of all these comments that we write during the demonstration on the example code. So you can go to the example code and get a more detailed version of all these comments. So the insertion itself is constant time. But to find the spot where it belongs requires us to perform this for loop search, this part. And we kind of baked it into the insertion algorithm. This isn't actually part of the insertion. Usually when we talk about the insertion, we just talk about this and then the consequences that happen beyond that. So a lot of the time you'll see these tables of what different operations are in Big O format, and there'll be an entry for insertion. That means just the actual insertion part, not the searching for the spot where it belongs. So, okay, it is O of 1 to insert something here. To insert something. But it requires an O of n, let's be capital, search to find the right spot. And it requires that every time because you don't know what the next available spot is going to be. So even though we've written the search into the function, if we were looking at the overall effectiveness here, it would be something like O of n because you have to find the empty spot, which is going to take you on average n over 2 searches. If the array is nearly full, it's going to take you more than that, but if we average it out, it's going to be something like n over 2 for all the items that you've inserted. And that's O of n in Big O notation. The more items there are, the longer it takes to find the empty spot where we belong. So the improvement that we can make is really simple. We can keep track of where the next spot is. And if we keep track of where the next spot is, then we don't need to do that search anymore. So we want to insert item in the first spot available, and this is O of 1 insertion with no requirements to do an O of n search to find the spot. So how do we do that? Well, the spot that we're inserting into, well, let's look it up again. Let's say that we're in this state, for example. Where do we insert next? Well, it's obvious that we're going to insert next over here, right? I mean, we're just going to insert into the next available spot. And the next one's go over here. It's just the next available index. That works perfectly well. If it's unsorted, so let's do that. Let's use a variable, we'll call it next spot, and it's going to track the next available spot for us to insert into. Of course, we start at 0 when the array is empty. And we'll just say r of next spot is equal to n, and then next spot plus plus. Okay, good to go, right? Let's try it out. So we're going to, oops, let me switch to my better version there. So I'm going to set use better to true, so that we're now using the better one that we started writing here. And a bunch of 4s, oh, look, everything looks pretty good. And now look, this little pink square is keeping track of the next spot. What's going to happen here? No more next spot, and we crashed. So obviously we went out of bounds here. We have to do a check to make sure that r of next spot actually exists so that we don't trigger an out of bounds issue there. So let's do that. If next spot plus 1 is greater than the length of the array, then we're not going to do anything. We're going to print this whole array is full, can't insert deal. And we'll just return. And then otherwise, we're going to go ahead and insert it. So just a little bit of an addition to our logic to handle that edge case of the array being full. And now we can add to our heart's content. And when we get to the end, it's just going to say array is full, can't insert. Notice I stopped one short. I like doing that for the visual here, but you actually could have gone all the way up to the end, so you didn't have to do array plus 1. We could have just gone with array or length minus 1. Okay, so that kind of visualizes it pretty clearly, I think. Now let's move on to the more challenging one. How do we insert in a sorted list? Okay. So with these, we were always just able to put something in the next available spot, and the next available spot was always at the end. With a sorted list, it's not enough to just put something into the next available spot. You have to put it in the correct spot. So there's an element of searching that's in there automatically. All right. And we also want to check, let's just handle that edge case right away, if the array is full, so that we can tell the user, give them that little error message and do nothing. And by the way, later on, we'll see what we can do if the array is full and we want to keep going. So that's going to be what we learn about when we get to array lists. All right, if r of r.length minus 1 is not equal to default, then the array must be full. Let's think about why that is. So if r of r.length minus 1 is the last spot in the array, right? If it's a sorted array, then all the spots must be occupied. There can't be gaps, because gaps wouldn't make sense for sort order. That's something we didn't really talk about too much when we were doing the unsorted ones. Technically, they could have gaps. We made them both so that they didn't. They just always insert at the end. But let's think about what happens when you start to remove things. Could you make gaps? Well, if it's sorted, you probably shouldn't have gaps. And actually, most arrays don't have gaps. And implementations of things like ArrayList under the hood don't leave gaps. So usually what you have to do when you're adding a new item is to shift all the other items over. And likewise, when you remove an item, you have to shift all the items back to fill in the gap that you've made. Let's talk first about this whole being full thing then. If you're inserting items every time and you're not leaving any gaps, then when the very last spot is full, since everything's in order and there are no gaps, that must mean that all the other spots are full too. So I'll just put this print statement there and return. Okay, so that handles the case of the array being full. Now, how do we insert something into a sorted array? So we did that example a little bit earlier with insert 2 and 1, 3, 4, 5, 6. So what you probably did in your head in order to figure out where this goes is you checked 1, is 1 bigger than 2? No, so we keep going. And then you got to 3, is 3 bigger than 2? Yes, it is. So this is the spot where 2 belongs. And since this is the spot where 2 belongs, everybody else has to shift over now. So the new format of the array is going to be 1, 2, 3, 4, 5, 6. So notice how everybody else actually shifted over to the right by 1 spot. Okay, so the first step in that is figure out the spot where it goes. So figure out, search for the spot where the value goes. Now remember I said that insertion doesn't count the searching, generally speaking, and that's true here as well. So the search algorithm that I'm going to write here is going to be an inefficient one. I'm going to write just loop through the length of the array, and when I find something bigger, that's the spot. So there are better ways to search, as we'll look at later, especially when we cover searching, but this is the most straightforward. So if r of k is equal to default, then we've gone too far. We've gotten past the area where there's data. In that case, it's easy. We just want that spot to be equal to the new value, and then we'll return. So if we pass, let's say, again, back to our example, which I should probably stop erasing, if we wanted to insert 7 into 1, 3, 4, 5, this is the case that we would run into. We would look at 1, we would look at 3, we would look at 4, we would look at 5, and then we would run into default over here, which is actually -1. And then we would know that we're in the right place now because we've gotten to the end and they're in order. Most of the time, we're going to insert somewhere in the middle though, not at the end. So if the number that we visited just now is smaller than the number that we're trying to insert, then we're just going to continue on. This is what we did when we were inserting 2. We said 1 is smaller than 2. 3 is not smaller than 2. So we're going to do something else in that case. What do we do in that case? Well, we're going to actually execute the insertion. So we found the spot at this point. At this point, we found the insertion spot. At this point, we got to the end of the data, inserting into the empty space at the end. At this point, we found the insertion spot, and we can break out of this while loop and then handle the insertion outside of it. And so if we're doing, let's say, so we did 7 earlier, that's going to go to this if statement first, when we're comparing against the 1. Is 7 bigger than 1? Yes. Is 7 bigger than 3? Yes. Is 7 bigger than 4? Yes. Is 7 bigger than 5? Yes. So we're looping again and again. Is 7 bigger than 6? Yes. And then we get to the default at the end here, and then it takes this branch instead, adds it to the end, and concludes. Okay. I'm going to leave that. I already deleted it enough times and retyped it. Okay. I will move it over here somewhere. Alright, so what do we actually do to execute the insertion? Remember, we don't consider this to be part of the runtime of the algorithm. This is the search for the spot. That's debatable, I should say. You could consider this to be the runtime of the insertion as well. But generally speaking, we're omitting search when we talk about insert. We're only talking about what happens after we've found the spot where something belongs. Because there are many different approaches to finding the spot where something belongs to. Okay, well, first we have to shift all of the other values to the right. So like when we were inserting 2 into 1, 2, 3, 4, 5, 6, it ended up being like this, 1, 2, 3, 4, 5, 6. Default, so obviously the values all shifted to the right to accommodate the new spot that was made. So let's shift values to the right to make a spot. Now you see why I use the while loop instead of a for loop, so that I could declare the value up here and then I would still have it down there. So now I have the spot where the thing is supposed to be inserted. That's called k. And if you'll remember back from your introductory programming days, if you tried to do this in the forward direction, then you would end up accidentally overwriting the spot. So if you tried to say r of I equals r of I plus 1, then r of I would become I plus 1, and then it would just kind of propagate forward. You've made this mistake in intro class, I'm sure. So we want to move from the back to the beginning and move things towards the right. So from the back to the point that we're trying to do, and then move things toward the right. So I'm starting at the end of the array. I'm starting at the second to last item because I'm going to be using I plus 1 in the body of this for loop, and I don't want to be able to go out of bounds. Remember, the last item in the array is length minus 1, so I want the second last item in the array so that I don't risk going out of bounds. And all I want to do is make that next value the previous one. And if I do that up to the spot where we're trying to insert, I've actually got a duplicate value there, but it doesn't matter because the next thing that I'm going to do is overwrite it with the thing that we're actually trying to insert. So I've moved everything over to the right. I've executed, auto formatter. I've executed up to this point with the for loop, and then this statement executes the actual insertion of the 2. But if you think about it for a little, after the execution of that for loop, what you really end up with is this, and it's only when I overwrite it with that 2 that that extra 3 goes away. But that's relevant because we did overwrite it. Okay, that's pretty much it. So we have inserted something in a sorted fashion now. I can delete this now, lovely. Let's switch to sorted. Why did I put that in another file? Terrible organization. All right, let's go. So I'm going to insert 4, 5, 6, 7, 8, and then I'm going to insert 1, and lo and behold, it goes to the beginning, and I'm going to insert 2, and lo and behold, it goes to the right spot. And then observe that this 4 is purple. Notice I gave them all a random color. Watch what happens when I put in another 4. You get a blue one there. How do you decide those? How do you decide if a tie goes before or after? Well, I used less than, so equals would resolve in favor of the finding the spot. So it's going to insert to the right in my case. This is fine, but it's something to consider when you're designing an algorithm like this. Do you want things to insert before or after? Before or after duplicates. And it should be consistent, obviously. So this one does after, and that's fine. All right. One more thing we need to do, though. We aren't tracking the next spot. Do we have to? Well, for insertion, no. But we're going to see later that it's actually quite handy to have it in some cases. And there is an optimization that we could make here if we had the next spot tracked. So anytime I execute this insertion, I'm going to keep tracking the next spot. And the optimization that we could make here is when we shift the values to the right, we could do this only starting at the last item, which we now know because we have this next spot tracker. So the next spot is now no longer actually the next insertion spot. It's kind of a misnomer. It's now the length of the actual data. So every time we insert something new into the array, we increment next spot by 1. Now we have the length of the actual data in the array instead of just the array. So the optimization that we could make here is that we could do our shifting to the right, or we could do our insertion only on the part that actually contains data. So we could, for example, instead of going k less than array.length, we could stop at next spot plus 1, which is the length of the data and then the very next empty spot, for example. We're not going to do that here because it requires you to do a little bit of extra manipulation to not go out of bounds, and we don't want to make it confusing. And we're going to see later when we get to removal that inserted removal, yes, inserted removal, sorted removal, I thought that sounded wrong, sorted removal, it makes sense to have this next spot tracker as well. It helps to know how large our data is for another optimization that we can make. Okay, so that is our insertion, 3 ways. Now let's go to our next item. So we're going to go back to unsorted first. Boy, I really should have moved that. So we're going back to unsorted first, and we're going to go back to the not better version, so the most basic one. So let's go to, I guess we'll do removal next. Let's go to removal. So removal, we'll start with the unsorted not good version, the simple version. Remember that in this version we don't have that next spot tracker. That was the only real optimization that we had made when we made the better version. So we just have a bunch of stuff in the array, and what we're going to do is we're going to find the spot that we can insert into, and then we're going to just set that spot equal to our new, or find the spot we're going to remove from, and we're going to set that spot equal to default. So that's all we do to remove. We're going to not worry about leaving gaps when it comes to removing in this way. So if we don't worry about leaving gaps, is that going to cause any problems for our insertion algorithm? Let's go back and look at it for a second. It's this one, the not better one. So if there are gaps, is this going to have any problem at all? Well, actually no, because it goes through the entire array and it finds the first spot that's default. If that happens to be a gap, it doesn't matter, it'll still find it, and then it inserts into that spot. So it actually works fine if there's a gap. But before we can do insertion, we actually need to tackle something else in I guess a more specific way. We're actually going to tackle search first. Because up here, we kind of baked search into the algorithm. Let's actually turn those into separate things. So we're going to start with the unsorted search. I mean, we already pretty much wrote this when we were doing the insertion, but here we go. This is the simple unsorted search, and we can't really optimize this because you don't know if a value is there or not until you've gone through the entire thing. Now, I didn't even make a better version of this, but I could have, where you only search the space up to the next spot. But for that to work, you have to have left no gaps, because otherwise you don't know when the actual array ends. We'll see why that can be a challenge. So if, there should be an if there, if we find it, then we're going to return the index where we found it. So this is going to return the index. Returns the index of the first item, the specified value, or default if not found. So we're going to leave this last return here. If we get through the whole loop and we still haven't found the item, then we'll return default. We'll return -1. And the runtime performance of this is obviously going to be O of n. And it's a bad O of n because, again, we have to go through the entire array every time, or at least all the data in the array every time, to tell you whether it's there or not, because it's unsorted. All right, so how do we use that for removal? All right, well, first I want to find where it is that it exists. So I equals search unsorted. And then I want to handle the case where it didn't find it. So if it didn't find it, then it would have returned the default for me, right? So if it's not equal to the default, then I'm going to do some stuff to actually execute the removal. And then otherwise, I'm going to return false. So what I'm indicating with true and false here in the removal function is true if something was removed, and false if not. That way you can get some feedback on whether or not your removal was successful. This is pretty common in the remove functions that are built into Java too. So like we'll go into ArrayList.remove later, and it does the same thing. It returns true if it was successful and false if nothing happened. So all we got to do here is set the index where we found that value to default. That overwrites it and makes it empty by the standard that we've set. So it is now empty, default. Let's see how this works in practice. Let's add some stuff. There's a bunch of numbers. I'm going to switch to removal mode. Let's remove 4. What's going on here? Did I forget to link this thing up? Are we using the right one? Let's see. Remove better. Use better is false. Is sorted is false. And what did I do wrong? Maybe my search is incorrect. We're off the script. don't want to have to go into the graphics. Let's see. Well, let's just print something out. See what we got. So we'll print out removing, do a little debugging, removing n, and then we'll print out where it found it. For simple programs like this, your print lines are going to be your best friend debugging. Alright, so we're trying to remove 4, removing 4 and it wasn't found. So I'm trying to remove 5, removing 5 and it wasn't found. It gave me a -1. Trying to remove 7 and it wasn't found. So something's wrong with my search down here. Something's wrong with my search. And what's wrong with my search is that I wrote it in the wrong place. I wrote it in search sorted. I meant to write it in search unsorted. So that was a really obvious error. I'm sure a lot of you saw that in hindsight now on the recording. That's what I get for leaving a bunch of placeholder functions. Okay, so that's pretty dumb. But let's keep going. All right. See how it looks like. Okay, so we inserted a bunch of items in no particular order. Let's try to remove 7. So it should get this one. It should get the first one, right? So switch to removal mode and yank 7, and there we go. And if we hit 7 again, it pulls another one, and you can see that it is leaving gaps. Okay, now if I try to insert again, so I switch back to insertion mode, I'm going to insert a 5, and it's going to fill the gaps. It doesn't care that there are gaps. And again, I can remove a bunch of crap, generate a bunch of gaps. And then I can switch back to insertion and continue to insert to my heart's content. So there is definitely some advantage to this unsorted version that allows gaps. But there are also definitely disadvantages to it. Remember, going back to the insertion, it requires an O of n search to find the right spot. This loop that we needed in order to find the first empty spot. That still remains true. What else? Well, the search takes a long time because the search requires us to search through the entire thing. So that remains true for removal as well because we need to find the spot where it belongs in order to remove it. So both insertion and removal require this search for the next available spot. And other than that, it's fine. It only takes all of one time to actually insert the thing itself. There's no need to shift anything around. So in that sense, it beats the sorted version a little bit. But we can make this better if we just use that next spot value that we had before. We can make it better by making sure that there aren't any gaps. If there aren't any gaps, well, first of all, our data looks more organized. It's definitely much better from data access point of view to not have any gaps. So almost all the data structures that you'll see in the wild have no gaps. Gaps are bad for the most part. If we use this next spot variable, we can do something similar to what we did when we were inserting better and omit the gaps with removal. Okay. Now remember that order doesn't matter. So we don't care whether or not an item is in the first spot or the 7th spot or the 10th spot. It doesn't matter for this unsorted array. And we also don't care if it's stable in this example. And stable means that if you have, let's say, 4 4s, there's the blue 4, the purple 4, and the pink 4. If I removed one, or if I removed something else in the list, the remainder would still be in the same order that they started in. It would be whatever I said, blue, then purple, then green, and then after removal, it'd still be blue, purple, and green in that order. We don't care about that either. It can be unstable. Those 4s can move around. They're all the same for our purposes. So if we find an available spot to insert into, and we don't want to lose gaps, then what we really want to do is backfill that gap with something else. Well, what can we backfill that gap with? Well, we can backfill that gap with anything. Why don't we just backfill it with the last item in the list? If we backfill the gap with the last item in the list, then we know that we can move the next spot down by 1, and we're always inserting at the end. Then when we insert, we don't have to perform a search. So we change our insertion. Where's my insertion at? We change our insertion to O of 1 time because we get to continue to do this. If we didn't eliminate those gaps, this wouldn't work either, because the next spot isn't necessarily the next empty spot. When you're leaving gaps behind, there are a bunch of spots in between that are available for insertion into. Alright, so in order to enable that O of 1 time insertion on the end, we need to empty out the spot where the thing is going to be removed from. And then we need to put the item that was in the last spot there instead. So what we want to do is actually take that spot where we're going to remove the item from and set that equal to the actual last item in the list. Next spot, remember, points to the next available spot, the next empty spot. So next spot minus 1 is the actual last item in the list. Then the actual last item in the list, which we just swapped with the one that we're about to replace, well, that one we can erase now because we don't need it at the end there anymore. We've already moved it into the spot that we have earlier. And then we can just remove one from the next spot because we've now removed one item from our list. And otherwise this is the same as the previous, where we're going to return false if we just didn't find the spot where it belongs in. So I think I already changed us to using better mode here. Yep, we're already on use better. So let's see how it works in practice. Alright, I'll move this over a bit so we can also see the function. So let me insert some stuff first in no particular order. Note the next spot chugging along there. Now let me go into removal mode, and I'm going to try to remove this too. And what's going to happen is that we're going to take the item on the end, the 0, and it's going to take 2's place. And then we move the next spot down by 1. So if I remove 2, 0 takes its place, and we move down by 1. And you can see 0 actually picked up the color of the previous one, because the color is based on the spot, not the number that you have. So 0 took 2's spot completely. It just changed that value to 0. The value is what we're actually storing in this list. And then that last spot just got set to empty. So if I removed 5 here, 3 would take 5's place, and then 3 would be removed from the list. That's actually how we're removing 5. We're putting 3 in its place, and then taking the 3 off the end. So boom, the 5's gone. Removing this 4, it's going to get replaced with this 4. And boom, it's gone. That one didn't change color. And then, let's see, removing this 2 at the very end, what's going to happen there? Is that the only 2 in the list? Yes, okay, so what's going to happen if we remove this 2 at the end? Well, nothing. It gets replaced with itself, so nothing happens. It got replaced with itself, and then it got removed. You removed the last item. So that handles that edge case where we're removing the last item. Let's remove everything else. 0, 3, 4, 5, 7, 8, 6, 3, and 1. Okay, we removed everything. Cool. And now there's nothing left to remove. We're done. Alright, and we can insert again. Okay, so that's removal in unsorted land. And that's obviously better because we haven't left gaps and because we got to have O of 1 insertion time. We're always inserting at the end. So by maintaining that next spot, that little pink outline pointer to the end, and making sure that that's always the next place that we have available, we can now insert with O of 1 time. We don't have to find the spot. It doesn't matter if there's 10 things in the array or a billion, we always know that that next spot is the one that's available. So before we move on to removing sorted, we're going to do the search for sorted as well. We'll do the search for sorted, and earlier we had done a kind of very straightforward search. We just did this thing where we started at the beginning and went to the end and looked through all the items in between. Let's do something a little bit more complicated. Let's do something with log n performance. So I talked about how searching through a dictionary or searching to find a page in a book is log n performance because you can use binary search. Well, we're going to use binary search here, and let's say a sorted array offers us better search options. Here's binary search, which which is O of log n. Our search unsorted is O of n. If we'd made it very slightly better, we could have only gone up to next spot, which would have still been O of n. Now we're going to get O of log n. Okay, so binary search works like this. We want, for the interval we're looking on, we want the start, middle, and end. Okay, so let's say that we start with 1, 2, 4, 5, 6, 7, 8, 9, and we are searching for 4. Yeah. Searching for 4. Okay, so the start is right there, the 1. That's the start. The end is right there. That's the 9. And let's make this a little bit easier. Let's make it an even number of items. So I'm going to add another 8 here. The middle, in this case, for the even number of items to start is going to be right there, the 6. Okay, so you've got your start, your mid, and your end. All right. The next question you want to ask yourself is is the midpoint greater than what you're looking for, or less? Is mid greater than what you're looking for, or less? So if we're searching for 4, then the mid, which is 6, is greater than what we're looking for. If it's greater than what we're looking for, then we're going to look to the left of the midpoint. If it's bigger than what we're looking for, then we're going to look to the right of the midpoint. And if they're equal, then we found what we're looking for. So we're equal. We're done. Okay, so if mid is greater than n, go right. Let's go left. So we're saying that 4 is less than 6. So we're going left. That means that we take this part here, and we know that the answer, if it exists, is somewhere inside of that part. The rest of it definitely doesn't contain the answer. Okay, so now this is the start, this is the mid, and this is the end. And it so happens that we found it. We found 4. So that's it. We're done. It only took us 2 iterations in order to find it. Or 1, you could say. Depends how you want to count the iterations. But let's say I'm looking for 2. Let's change it. Let's say I'm looking for 2. So in this generation, I still haven't found it. 4 is not 2. So in this generation, 2 is less than 4. So we're going to go left again, which leaves us with just this part. What we end up with is this right there. And that's the start, that's the mid, that's the end. And there's 2, the new midpoint. Now let's say we're searching for something that doesn't exist, like 0. How do we know when we're actually finished? Okay, so it was smaller, and then in this generation we would have split to the left again. We just end up with these 2. When you're ending up with 2 values left, either the first or the last is also going to be the midpoint, so that's how you narrow it down at the end. And then in the generation after that, the start is actually going to pass the end, and then we know that we're done, because that doesn't make any logical sense. We've gone too far. So we stop when we get to the point where the start pointer, this guy, passes the end pointer, that guy, or the end pointer comes before the start guy, whichever way you want to think about it. All right, let's express this in code. This is best done with recursion, which we'll learn about later, but you can also do it in the old-fashioned way, which we'll do today. So we want to start, we want an end, and we could optimize this. This is where it helps to have that next spot. We only need to look in the interval where there's actually data. In fact, our search won't work very well if there's a bunch of defaults on the end here, because they're not even sorted. They're all technically -1, right? So they're not even in the right place if we're thinking about sorted order. They don't belong to the data, so they don't get sorted. But if the end was over here, well, that would move the midpoint to around 8, and then we just have this extra stuff on the right side that makes our algorithm less efficient and doesn't help us. So it helps, that's where that optimization comes in handy on the sorted list in particular. And then the midpoint, which I'll just call I for simplicity, is obviously just smack dab between those two, so start plus end -2. -2 divided by 2. Whoopsie, don't want to format yet. So I didn't give you the indices here, but obviously the indexes are 0, 1, 2, 3, 4, 5, 6, 7, 8. So if the start is 0 and the end is 8, then, well, the end point is 8 plus 0 divided by 2, index 4, right? And you can just go on your own time and verify that that's true once you drill into the second half here. If you were searching for something in the second half here, the midpoint would be 8 plus 4 is 12, divided by 2, that's 6. So you can see that 6 is the midpoint of the second half. All right. So that's the midpoint in the first generation. And I'm also going to keep track of how many generations that it takes so that we can print this out, just so you can see that it doesn't expand very much and that we can actually find any number within like a single-digit iterations. And this is actually true even if we make the array much, much bigger, even if we made it like 100 items. So remember I said that we're going to stop when the start passes the end, or the end goes before the start. This might make a little bit more sense as we actually get into the algorithm. So if the thing that we're looking for is smaller than the, whoopsie, that was bad. If the thing that we're looking for, if the midpoint is smaller than the thing that we're looking for, then our start changes. If the midpoint, R of I, is smaller than the thing that we're looking for, then our start changes. So if your midpoint, 6 here, is smaller than the thing that you're looking for, so let's say you were searching for something in the second half, let's say 8 or 9. If your midpoint is smaller than the thing you're looking for, then the new start is now right there. So I did a little bit less of an optimization than this when I spelled it out. I actually cut off the whole area, including the midpoint, right? That's good for visualization, but we actually don't need that midpoint anymore because we know that's not it. We already checked it. So we can actually go one step better and say that this is the end now, and then we can pick the midpoint. Usually we round down. This algorithm's going to round down and say that that's the midpoint when there's an odd number of items. And in this case, we're actually not going to do another generation. If we were looking for 2, we found it. The only reason we do another generation is if we were searching for 4. Okay, so if we were searching for 4, and we had this, then how would we do the cutoff? Well, it's going to be on the right, and now we don't need to include the midpoint anymore because we know that that's not it. So we're actually left with just 2 numbers. We're actually just left with 4 and 5. And one of these is going to be the start as well as the midpoint. And that's going to be 4, and we found it at that point. So hopefully that makes sense. It's a little bit harder to wrap your head around when you're cutting off that midpoint each time, but it should be pretty intuitive to understand that obviously we don't need to include the midpoint in the next generation because that can't be it, because we already checked it. Okay, so that handles cutting off the midpoint for the start. We also want to do the other side. So we want to do else the end is I minus 1. So that handles the cutting off of the midpoint. If we're taking the first half, right? So if we're taking the first half like we did here, then we cut off the midpoint 6. So we take I minus 1. The midpoint was right there. We cut it off with the second generation. And then we also missed one other condition. We missed the case that they are equal. So we missed the case where the midpoint equals the thing we're looking for. In that case, we found it. We're done. Just return it. And that's pretty much the whole algorithm. Okay, if you get to this point down here, oh boy, did I leave an extra? Yeah, extra open paren somewhere. If you get to this point down here, then you haven't found it. Then you haven't found it. So we have to say like, well, you're not found down here. Because once those pointers pass, we're done. You don't have to do any more iterations of this. And this part where the pointers pass might be a little bit more obvious when we redo this in its recursive way. So if you don't get that right away, don't worry about it too much. All right. So with that in mind, I'm also going to print out how many generations that it took. So let's say this is binary search, iterations, print out count, and then every time we'll do count plus plus. And then we'll also, let's print out all those values so we can visualize it a little better. So we're going to do start, I'll do end next, and I'll do midpoint last. End plus mid plus I. Okay. So that should help us to visualize it a little bit better. All right, that gives us the search. But remember, this was all part of removal. It was all part of removal. We could also apply this to insertion. We could go back and fix our insertion here to find the spot where it belongs with binary search instead. But that's a little bit more complicated because in that case, we're actually not sure if the value is there or not. If it's not there, we still want it to find for us the spot where it belongs. That's a slightly different question than finding whether a value is there or not and removing it if it is. So it's going to take a little bit more thinking for us to modify our insertion. We're not going to do that today, but it's something you can think about. All right, so let's get to the removing a sorted item. Now you've already probably expected that we're going to have to shift all of the values to the left to accommodate the gap that we've created. And you probably note that we could just use the unsorted search. Although it is slower, it's O of n performance. It would work perfectly fine here too. So, same deal. If we found it, remember we return default if it wasn't found. Then we're going to do some stuff and return true to indicate that we hadn't inserted it. All right, so what do we actually have to do? Well, if we had to shift everybody over to the right when we inserted everything over, then of course we have to shift everything over to the left now. So left shift all values beyond that point. All right. For int, well, here I will use k since I already used the app. All right, for k equals I, k is less than r.length. Again, we could optimize this since we use that next spot. We could stop at next spot. We don't have to shift beyond that. I'm not going to do that here because we still have to accommodate the array boundaries. So there would be an and there, and I think it's a little confusing. We'll just keep it simple for now and shift them all over. We'll just shift over up to k plus 1. Okay, so we could make things, again, a little bit better by only left shifting up to the next spot. All right, now we know that the next spot should be blank. So, how do we handle that? Let's think. So we left shifted all of the values beyond the point where we're going to remove the item. Let's maybe demonstrate this, make more sense. All right. 4, 5, 6, 7, 8, 9. Let's say we want to remove 5. So we remove 5, we left shift everything else over. 6, 7, 8, 9. Okay, but when we left shifted everything over, did we left shift this last spot here? Well, if there was an empty spot beyond it, like if it looked like that, then yeah, we would have left shifted the default over because we didn't stop at next spot. But if there wasn't, like if the list was full, then nothing would have come in from that last spot, and we would have a duplicate 9 on the end there from everything left shifting over except that last 9. So removing the 5 was actually already accomplished by doing this, because we just left shifted over it. We overwrote it with the thing that was to its right. Now we got to get rid of this last spot here in the edge case. So let's run it without doing that and see what this looks like when it goes bad. I think I've got everything on sorted mode right now. So let's do 1, 2, 3, 4, 5, 6, 7, 8, and then we'll insert some 4s. Whoops, that's still unsorted. All right, 1, 2, 3, 4, 5, 6, 7, 8, and then let's insert some 4s. Look at them go in the middle there. Some 5s, they go in the middle there. Some other numbers, whatever. Let's fill her up. Okay, so it's full now, and I am going to try to remove, let's say, this first 3 here, or any of the 3s. Whoops. Well, I went out of bounds, didn't I? Let's see where I went out of bounds. I went out of bounds right there. Right there. So that was actually just a bug. I forgot to include the -1 for the left shifts, and I went to that +1 here. So that was just me forgetting to stay within my array boundaries. All right, let's run it again with that fix in mind. Okay, I filled it up, and now I want to remove this 3. Ooh, my binary search seems to have a problem with it. All right, let's stop that. Let's see what's wrong with my binary search. Oh, did I forget to move the start and the end pointers? Let's see. Oh, yes, what did I forget to do? I moved the start, I moved the end, but I forgot to update the midpoint. Whoops, so in every generation, of course, you gotta update the midpoint. So it's not enough to move the start and the end after you move the start and the end. Now you gotta calculate the new midpoint accordingly. Whoops, all right. Hopefully this one demonstrates the problem with our remove sorted functionality. I'm demonstrating other bugs instead of the bug I want to demonstrate. Okay, we're going to remove this 3 here, and we did it, but lo and behold, we've duplicated the 8 on the end, and let's remove this 3 here. So that 4 is going to move over, this 5 is going to move over there, that 6 is going to move over there. Everything's shifting to the left, but we're going to have 3 8s on the end instead of 2. So we remove that 3, and whoa, we have 3 8s. So that's definitely a bug. We'll fix that in a second, but I want you to direct your attention to the binary search, which is actually kind of hard to read at the moment. So let me go ahead and add a little console print somewhere. Let's see. Let's add where do I want to put it? I want to put it before the return, maybe? Yeah, let's do that. Let's do just a blank line here so that these are separated, because I don't want these all bunching together. Makes it too hard to read. And let's fix that bug while we're already here. So how do we remove that bug? Well, we want to empty out that last spot on the end after we finish left shifting everything over. So if the next spot is all the way over there, so it's at the end, it's the last spot, then we want to empty out the last spot. And we also forgot to decrement the next spot every time we update, which will help us keep track of it so that we can keep getting this efficiency gain, and also so that we can keep binary searching correctly again, because remember, we use that next spot to delimit the area that we should search into, so it improves our efficiency because we don't have to search all that empty extra space. Alright, so that should fix the bug there. Let's give it a shot. I'm going to try to remove 7, and I'm going to try to remove 7, and that did not fix it. What did I forget to do? Oh, I forgot to actually set the spot equal to empty. Duh, okay. Okay, alright. And this catches the edge case where it's at the end. Alright. Well, at least we're learning a lot about catching bugs today, too. Okay, now when I remove the 4, I also remove that last spot there. Okay, so to the binary search then, let's have a look. How did it find that 4 for me? The 4 was towards the beginning here. So in the first iteration, the end was 20, the last index, obviously, and the last index is 19, not 20, so keep that in mind. The midpoint is 10, and the start is 0. In the next generation, the end is 9. So remember, we cut off the midpoint. We don't actually need it, so we take just everything to the left of it, 0 through 9. The midpoint is 4. So that was between about here and 1, 2, 3, 4, 5, 6, 7, 8, 9 items over here. And the midpoint was about there, which is 3. That wasn't quite what we were looking for yet. And then we took the next section, which was between 5 and 9, and the midpoint was the 7th item, so that's the 1, 2, 3, 4, 5. So between here and 1, 2, 3, 4, shoot, that's 5. Between here and 6, 7, 8, 9. So between the 3 and the 4 there was we were searching. And the midpoint happened to be a 4, and so we removed it. And so something that you can see here is that it's definitely not stable. It's going to find a 4 for you, but it might not find the first 4 for you. It's going to find a 4. The 4 that it finds depends. It's going to give you the first valid midpoint that it finds. So it depends completely on how it's split into segments, and you might not necessarily get the first occurrence of a number. You'll just get an occurrence of the number. So if removing the first occurrence of the number is important, then you can't use this kind of search. But I shouldn't have said that it's not stable. That's actually not entirely true, because the rest of the 4s and the rest of the 7s and the rest of the 5s, anytime you remove a 4, they all stay in the same order. Which 7 is going to be removed if I remove here? Is it going to be this green one, this light green one, this red one, or this lime green one? Well, let's see. Okay, it was the lime green one, actually, the one at the end that got removed. Well, which one is it going to be here? Is it going to be the one at the end, or one of the first 2 here? It's actually the one at the end again, and the one at the end again, and the one at the end again. So in this case, it was always the one at the end. All right, how about which 4? The teal one or the gray one at the end? Oh, the one at the end. The one at the end. How about which 5? The one at the end. The one at the end. Actually, I think that's because of the color of the boxes matches their spot. So now that I think about it, that wasn't a very useful example. My bad. But yes, you can't guarantee that it's going to remove any particular one, but the others that are left behind are going to remain in the same order. All right, so what do we consider that removal to be? A question for you to consider. What do we consider that removal to be? Well, the removal process, not counting finding the thing that we're supposed to remove, so not counting the search, is the same as the insertion. We have to, on average, move about n over 2 items over to the left, so this is still O of n removal time. But because the search is so much faster, and because search dominates our usage, we tend to use search a lot more than we tend to use insertion and removal. Generally speaking, your priority is going to be to optimize the search and the access functions versus the insertion and the removal. And having your array in order is obviously an advantage for search. So generally speaking, your sorted in-order array is going to perform a little bit better than your unsorted. But as we've seen here, the fastest insertion time is actually still on your unsorted array, which backfills the gaps and always keeps track of the next available spot. Although the only way to search that one is to exhaustively search through the whole thing, it does have quick insertion. So if you want the academic answer for how long it takes to insert something in an array, it's really this one. Even if it's not a sorted array, this is typically how people will do it. They will not leave gaps, and they will shift units over to the right as needed. If it's unsorted, then you can insert at the end, which is faster. But in that case, as we'll see with array list, the O of n can come from the fact that the array has to grow once you reach its limit. But if it's unsorted and you can insert at the end, then yes, you can achieve O of 1 time. But usually, when people are talking about inserting into an array in the context of most of the big O tables that you're going to see on the internet and most of the big O conversations, they're talking about this, where you need to squeeze everything over in order to make room for the new item. Likewise, for removal, we're talking about squeezing everything over to backfill gaps, because generally we don't want arrays with gaps. And for search, well, that depends. We're talking about, sometimes we like to say exhaustive search, and for that we're talking about this one, going from start to finish, if it really is unsorted. Sometimes we talk about searching a sorted array, or the best case sort. In that case, it's fair to say log n, although there are better algorithms than binary search. There aren't many that are much better, so this is pretty darn good. O of log n is very, very hard to beat, especially for very large amounts of items. And then I also want to keep in mind that there's sort as well. And we'll talk about sort obviously much later, many weeks down the road. But if you do need to use sort for whatever reason for any of your algorithms, remember that there is simply an arrays.sort that allows you to use the built-in sort. And if you hover over the documentation for the built-in sort, you'll see that they tell you that it offers O of n log n performance. And it uses something that we're going to learn about down the road, which is called quicksort. But something to keep in mind is that the sort requires O of n log n performance. So you could sometimes make things like insertion faster by simply sorting the list beforehand. So some algorithms that you might apply for insertion are something like put the item on the end of the list instead of having to find its appropriate spot, like this. You can just put the item on the end of the list and then call your sort function. So we said that this was O of n, and sort is about O of n log n. So you're actually not doing that much worse by putting it on the end and then calling the sort function. And then you don't have to think about any of this stuff. All right, hopefully you were able to follow along with that and enjoyed it. Next time we will cover array lists, and I will see you then.